All right, so up next, modules in Nashorn. I'm Michael Haupt, and I have the honor of standing here instead of Sundar, who can't be here. Don't ask me any questions. This is not work I did. I'm only representing, so don't shoot the messenger. In fact, ideally, if you have questions that are about the Nashorn thing, I can try to answer them. If you have any deeper detailed questions about the modularity aspects of this and the jigsaw aspects of this, I can only second what Alex just said and ask you to take that to the modularity workshop later today. This is an important slide. One day somebody should sing it so it's more memorable. Still working on the music, maybe next year. All right, so topics. The Nashorn implementation in Java 9 is modularized. It relies on the jigsaw abstractions already. And I'm going to first give an overview of Nashorn as such and the rough bits of the architecture. I'm then going to cast a look at the class loaders that are in use. There are various kinds of class loaders in Nashorn. That sort of continues the intro. And then we get to the really interesting bits in the section about dynamic modules and cross-layer exporting and reading. That's where module creation at runtime and how modules make it possible to isolate bits and pieces dynamically at runtime from each other will be covered. So this talk is interesting for language implementers. Well, it's about a language implementation. And apparently there have been questions from the implementers of other languages that run atop the JVM as to how Jigsaw can be dealt with and how JDK 9 features can be used for the best purpose. So overall, how can I shape a language implementation atop the JVM, starting in JDK 9, in the days of Jigsaw, to support encapsulation and security in that implementation? So Nashorn. Well, it's, as you might know, a JavaScript engine. It's fully ECMAScript 5.1 compliant. It has been around since JDK 8. It does have partial support for ECMAScript 6. Parsing is fully supported. The features are not all implemented. Feature implementations are coming up. Take a look at JEP 292, which is a good number. And there are more details about that. Incidentally, the ECMAScript 6 parsing capabilities are there thanks to Graal.js. So the Nashorn implementation has adopted the ECMAScript 6 parsing capabilities that have been implemented there in Graal.js. And it goes all looping back because the Graal.js parser started out as the Nashorn parser. So that was what the Graal.js project started with. Nashorn is usable in many different ways. You can use it through the javax.script API purely programmatically. You can use it as a standalone JavaScript engine through the JJS executable, and also as a REPL, if you just run JS without any arguments. It also extends JavaScript with some scripting features. So it supports shebang notation, so if you have a JavaScript file and put the shebang and the path to your JJS executable on the first line, you'll be able to run it just like a shell script. And the shell script, which you can also programmatically enable on the command line with the -scripting argument, enables some interesting features such as here docs in JavaScript and escaping out to the shell to execute operating system level binaries and such. Also piping of processes that you spawn from inside JavaScript. So it's fairly interesting to write scripts in JavaScript that way. Java interoperability has been a big thing ever since, and naturally because Nashorn, written in Java, runs on the JVM, it does make sense to also reach out to Java. Java Interop is really almost seamless. You can talk to any Java class, all Java objects that obey certain rules, has to do with accessibility. I'll come to that later. Security is fine-grained, very well controllable. You can give specific permissions to specific scripts based on the URL, say, location of the scripts in the file system and such. So not all scripts are sandboxed. Also, not all scripts are fully trusted. The user can choose to give specific permissions to specific scripts based on the location. Then the javax.script way of using Nashorn is also compliant with the compact 1 profile of the JDK9 module system, meaning there are very little dependencies that need to be fulfilled for that to be usable. An overview of the modules that constitute the Nashorn system. The jdk.scripting.nashorn module contains the runtime. This is also the module that constitutes the Compact 1 compliance. It relies on only very few external modules. Java.scripting, obviously, jdk.dynalink, and java.logging. The dynalink module is sort of special because it initially was placed, initially was part of the Nashorn implementation itself, but then was taken out and placed in the JDK as a separate dedicated module. Dynalink is also exposed from the Nashorn runtime module so that it can be used for interaction with other language implementations if need be. Two other modules that contribute to Nashorn, the JJS shell module, that's essentially the source code of the JJS executable. This is not Compact 1 compliant anymore. That's only true for the embedded Nashorn, but it still is possible to start a Nashorn REPL in a Compact 1 profile by running java jdk.nashorn.tools.shell. You don't get line editing and such, but it's still a REPL for JavaScript. Dynalink, as mentioned, has been taken out as a separate module in JEP 276. The source code is still in the Nashorn repository because it originated there. It's being maintained in that very place. So these are the three modules that make up the overall Nashorn thing. Some remarks on the execution approach. We do not interpret anything. Everything is compiled to Java bytecodes, then loaded as class files. We use ASM for that. The JDK internal ASM is used. For most of the basic operations, invoke dynamic is used. So everything is really late bound, thanks to Dynalink. This is possible. The only calls that are linked statically are those to the runtime where we know how the resolution looks. I'm not going to go into much detail about Dynalink here and now. There is going to be another talk on Dynalink tomorrow in the same slot. So the APIs that are exported from Nashorn. First of all, we have the javax.script API. That's the usual API that you need when you want to programmatically access a Nashorn engine. Then we have the scripting API, which implements things that are missing in javax.script, and that is Nashorn-specific things. So for instance, for script object mirror and JS object, very fine-grained access to properties, to check if something is a function, et cetera, et cetera. So it's language-specific reflective capabilities that are provided by this extra scripting interface. The tree interface, tree API, allows you to reason about JavaScript sources in Java or JavaScript, thanks to the Java interoperability. It fully supports ECMAScript 6, but recall this is parsing only, right? This is not the ECMAScript 6 implementation. This is really just parsing and AST access. The linker API exports the Nashorn internal dynalink linker. And if you want to exploit that, it's possible to have a tighter cross-language interoperability if, say, JRuby or Groovy wanted to interact with the Nashorn JavaScript implementation. They could use the dynalink linker to enable them to handle Nashorn property access and method calls and such. Right, these are the interfaces exported from Nashorn. And I'm now going to give an overview of what the Java integration is all about. So from JavaScript running in the Nashorn engine, you can access any public member of a public class in Java that's visible. Access checks are in place. Warnings will be given, exceptions will be thrown. And also what's particularly nice about the Java integration is that Lambda expressions and functions, JavaScript functions, are sort of merged into one here. So if you invoke from JavaScript any Java method that accepts a Lambda, then you can pass a JavaScript function in that place. Reflection is impossible. It's not possible to do any access to the Java lang reflect package from within JavaScript. The same is true for Java lang invoke. No method handles. This serves security purposes. Java extend allows you to subclass and implement Java classes and interfaces in JavaScript. What happens under the hood here is that Nashorn creates so-called adapter classes so that JavaScript objects can pose as objects responding to the implemented Java interface or the extended Java classes API. We cannot use Java lang reflect proxy because it's in Java lang reflect, so we need another way of doing that. Those adapters can access the Nashorn runtime for internals. User code cannot. User calls are all linked by dynalink, which uses the public lookup by default. And that means we can't access the runtime. Caller sensitive, should expand on that a bit. So dynalink calls apply to a call site that has a specific lookup object associated with it. The dynalink method handles are all resolved through public lookup. So caller sensitive would fail because public lookup is typically not what caller sensitive accepts. But dynalink takes care of passing the correct lookup object through the call, from the call site, through the infrastructure, and to the caller sensitive method. So that's all taken care of. Security. We have a dedicated sandbox for JavaScript execution. All the scripts, all the invocations that go through the Java x.script interface, no matter what the security domain of the Java caller is, will end up in the Nashorn specific security domain. And the the permissions are not inherited. So Nashorn imposes its own secure view on the world there. The Nashorn module is loaded by the platform class loader. It has all permissions it needs. But as mentioned before, it's possible to control in a very fine-grained way how scripts are trusted or not trusted. And if you're interested in how this is done, it's done with security policies. You can take a look, for instance, at the testing scripts in the trusted directory and the non-trusted directories of the Nashorn testing sources. Scripts in the trusted directory are then executed with all permissions set. So much for the rough background on Nashorn. I'm now going to take a look at all the various class loaders at play in Nashorn, each of which is contributing its own bit to the overall story. So before we get to the loaders in particular, one last architectural bit. This is the background before all the loaders and also later the modules operate. The context class holds all the relevant information constituting one Nashorn instance. There is a one-to-one mapping from instances of the context class to a Nashorn script engine instance. There may be many such instances in a single Java process, but they are effectively isolated from each other. The javax.script API can be used to control Nashorn engines from Java code. And yeah, I already mentioned that the context instances map to script engines. So there's this one-to-one correspondence here. Class loaders. So there are three different kinds of class loader at play in Nashorn. And the first of them is the structure loader. There is a single instance of that one per process, and it's responsible for all the engines and all the contexts, consequently. The structure loader is responsible for managing the script object structures of all engines. It creates objects, classes, that can be instantiated, and the objects have then optimized layouts. And to Nashorn and any JavaScript, they look totally natural. They're just script object subclass instances. But they are created with a specific layout so that certain fields can be better aligned and accessed. Up next, the script loader is responsible for loading the script classes generated by the Nashorn JavaScript source to class file compiler. By default, there is one such loader per script. This doesn't have to be the case, but this is the default. And so consequently, there can be many such loaders in one Nashorn engine, depending on how many scripts are loaded. Each script loader delegates to the structure loader, which in turn delegates to the platform loader. So thereby, all the structure classes are effectively shared, and all the platform classes as well. There is one little exception. Sometimes script classes may be loaded by unsafe.defineAnonymous class. If a JavaScript script is broken down into more than one Java classes, this may be due to size, for instance, all of them must have the same class loader, and they may have to access each other by name, the generated classes, that is. If they do not have to access each other by name, the unsafe define anonymous class trick can be used, and method handles are used to reference the JavaScript functions defined in those classes. This allows for very fine-grained unloading of script classes. So you can think of it as an optimization. In the end, there has to be one little dummy class loaded by a script loader that is used as the host class in loading all these classes in define anonymous. The third class loader is the Java adapter class loader, or rather, this class is the generator for loaders responsible for everything loaded due to a java.extend call. Remember, that's when you implement in JavaScript a Java interface or subclass some Java class. So this is a generator. The actual loaders are instances of dynamically created inner classes to this. The parent loader, it's not that simple. We have to find a loader that can see all reference types in the supertype or interface implemented. So if we implement some foo type and that has a method returning bar, we have to find a loader that can see both of them, which means we may have to walk up some part of the class loader chain until we find that. That loader is then used as a parent to the adapter loader, so that the generated adapter class can see all the required reference classes. This will often be the thread context loader, but can also be another. It's determined on an individual basis as a supertype combination is met. So we end up having one loader per such supertype combination. On to modules. The modules add, so to speak, another bit of access control around the class loaders that we have seen so far. We need dynamic modules, that is, modules that are created at runtime. Other than with a module info.java file, these are entirely created at runtime. The reason for this, everything that is not in the jdk.nashorn.api whatever packages is concealed, internal. However, compiled scripts, structure classes, and adapters need to be able to access some of the Nashorn internals. Unnamed modules can already access the named Nashorn module. But those internals are in a named module. We also want to make sure the scripts and structs are only accessible from the Nashorn module. So it goes both ways. So we don't want stuff in scripts and structs to be exported to the world, because those contain internals. It's fine for adapters, because they have only one package with a single public class. I'll come to that again. In the end, we need named modules. And the consequence of that is that the sometimes named individual modules created dynamically provide good isolation granularity. Different modules are well encapsulated. So we don't want Nashorn internals, recap, to be available for random code, and we do not want scripts and structs to be accessible by the world. Modules help us enabling this. The solution, the struct loader and the script loaders create named modules because they need fine-grained access control. Adapter loaders have unnamed modules because, again, there is only one single public class anyway. That can be exported, that can be seen by anybody that wants it. Layers. As seen before in Alex's talk, layers essentially map modules to class loaders. Creating modules is possible through the layer API, and we want to associate those dynamically created modules with the Nashorn source modules, which live in the boot layer. The boot layer configuration can, however, not be modified, so we cannot add new modules at runtime to that. It's fixed. So we need to create new layers. also dynamically. The structure loader defines the structures module in a dedicated structure layer. Each script loader has its own dedicated layer, and unnamed modules in the adapter loaders are layerless by default. Regarding the child-parent relationship between layers, these are organized in the same fashion as the class loaders. Final details of access control enforcement thanks to modules. So we need to do some access control and to isolate all those scripts from each other and the various elements of the implementation from the outside. In JDK 8, including the recent updates, the package.access mechanism was used for this. Package.access is this half-documented system property that you can use to give access to certain packages from other certain packages. Don't try this at home. What we did in 8U is we mimicked encapsulation using the package.access plus a security manager. But security managers are really not about encapsulation. They're about security. So it's a different thing. The package access thing is really a security manager hack to enforce encapsulation. And by putting some of the Nashorn core packages on that list for package.access, this was made possible. In JDK 9, we have much, much better encapsulation thanks to modules. It does not depend on the security manager or any such standard policy. It's just all thanks to the module mechanism. And the security manager can focus on doing what it's supposed to do, caring about security. So reviewing the access control requirements that we have in Nashorn. The Nashorn runtime should be able to access script classes, structure classes, adapter classes, and vice versa. Also, script classes and adapters should be able to access structure classes. And we don't allow any access between individual scripts, classes generated for the individual scripts. To put these rules to action, we need to make the access rights known. These are expressed as the reads relationships, so to speak, between the modules. We use dynalink, which means we deal with method handles, which means we have lookup objects and access control through lookup objects and contexts everywhere. We only want accesses between named dynamic and Nashorn modules. We do not want accesses from named dynamic modules to other named dynamic modules, the script modules, that is. And because we cannot express these relationships statically as we are creating the modules dynamically, we use the reflective API of the JavaLang reflect module class and the add reads and add exports methods on that class. Calling add reads, it's possible to let the receiver module read the argument module so that the receiver module can then access the public package members of the argument module, the exported members. Calling add exports, the receiver module exports an argument package that's given as a string to another argument that's a module, so that the argument module can then access the package contents. The module graph manipulator class mentioned here is part of Nashorn. And the structure loader and all script loaders load this class individually. And in its static initializer, the required add reads, add exports calls are done. Finally, the Nashorn module exports internal packages to generated code that is loaded by script loader, etc. And takes care of adding the required read links. Creating method handles is possible only if the module access rights are correct. So we need those read links between the dynamically created modules. Adapter modules, as mentioned, are unnamed. That is, they read all modules and they export their public elements. We do not need sophisticated mechanisms including named modules, as each adapter loader will only ever have one package with one public class in it. Point being, if you need to deal with this kind of access control, if there is nothing worth hiding in a module, use an unnamed one. And Nashorn takes care of exporting to unnamed modules, again, via the add exports. This call is also possible with an unnamed module as the target module. All right, this has been a whirlwind tour.